The broadcast is now starting. All attendees are in listen-only mode.
Welcome, everyone. On behalf of the Southern Alliance for Clean Energy, I'd like to thank you for joining us for today's webinar with the co-authors of the book Fukushima, The Story of a Nuclear Disaster. My name is Erin Cameron, and I'll be the acting facilitator for today's webinar. I'd like to take just a moment before we get started and review your control panel with you. You do have two options for audio, telephone, or mic and speakers through your computer, so make sure you have your chosen mode selected on your control panel. Also, if you would like to minimize your control panel, just select this orange arrow, and then you can select it again to display your control panel again. To ensure sound quality, all of your lines have been muted for this presentation, and we encourage you to please chat in your questions throughout the presentation using the questions option on your control panel. We will then answer the questions at the very end of the presentation today. For those of you not familiar with SACE, we are a regional organization focused on promoting responsible energy choices that create global warming solutions and ensure clean, safe, and healthy communities throughout the Southeast. We are a membership organization, and I would like to acknowledge our members on this call today and encourage those of you who are not members to please join us today. For ways in which you can become a member and get involved, please visit our website, www.cleanenergy.org. And I would now like to turn the presentation over to Sarah Barzak, SACE High-Risk Energy Choices Program Director.
Great. Thank you, Erin, and thank you everyone for joining us today. My name is Sarah Barzak, and as Erin said, I'm the High-Risk Energy Choices Program Director with the Southern Alliance for Clean Energy. I am really pleased to present today's speakers who co-authored a riveting book released back in February, Fukushima, The Story of a Nuclear Disaster. And you're looking at the cover of the book there in that slide. They will discuss the accident and findings in the book, along with the implications the Fukushima nuclear disaster has had here in the United States, along with concerns that remain, including those regarding the new reactors under construction in Georgia, South Carolina, and Tennessee. We will begin with Dave Lochbaum, Director of the Nuclear Safety Project at the Union of Concerned Scientists, or UCS. Dave is a nuclear engineer by training and worked at nuclear power plants for 17 years. He left the industry in the early 1990s after blowing the whistle on unsafe practices and joined UCS in 1996. Dave monitors ongoing safety issues at U.S. reactors, testifies before Congress and the Nuclear Regulatory Commission, and provides informed analysis of nuclear plant conditions and incidents. We are very fortunate to have access to his knowledge, expertise, and as many of you know, his wonderful sense of humor. Our second speaker is Dr. Ed Lyman, Senior Scientist with the Global Security Program, also at UCS. Ed is an internationally recognized expert on nuclear proliferation and nuclear terrorism, as well as nuclear power safety and security. Many of you know Ed from expert analysis he's provided on a host of nuclear issues here in the Southeast, including mixed oxide fuel, also known as MOX, and reprocessing, small modular reactors, and the vulnerabilities of ice condenser reactors, among others. He joined us in Atlanta in February for the initial release of the book, and we are really happy to have him join us again today. Our last speaker and co-author of the book is Susan Q. Stranahan. Susan was the lead journalist of the Philadelphia Inquirer team that was awarded a 1980 Pulitzer Prize for its coverage of the 3 Mile Island accident. For 28 years, she was a reporter primarily covering environmental issues at the Inquirer. She is the author of Susquehanna, River of Dreams. Thank you so much, Susan, for joining us today. Please note, as Erin said, that we'd like to get through all the presentations before taking questions. Now I'll turn it over to Dave Lochbaum with the Union of Concerned Scientists. Dave?
Thank you, Sarah, and thank you, Erin, and thank you, everybody, for participating in the webinar today. Next slide, please. My role today is, next slide, please. My role is basically a foundation for how the accident occurred. Ed and Susan then will follow up with what some of the implications are for here in the United States. Next slide, please. Next slide. Okay, Fukushima on March 11th, 2011 was a 6-reactor nuclear power plant. 3 of the reactors, units 1, 2, and 3, were operating. Units 4, 5, and 6 were shut down for scheduled refueling and maintenance outages on that day. The picture on the left shows the plant site before the accident. The picture on the right shows the plant after most of the damage had been done. Next slide, please. The accident started with a fairly large earthquake located offshore northeast of the plant. That large of an earthquake caused all 6 of the reactors at the site to lose their connection to the offsite power grid. So they lost their normal supply of electrical power to pumps and motors and fans that provided normal cooling for the reactor core, the spent fuel pool, and essential buildings. The 3 reactors that were operating at the time of the earthquake were automatically shut down within seconds by the shaking caused by the earthquake, and their emergency diesel generators automatically started up and were providing electrical power to the essential equipment needed to cool the reactor cores. But less than an hour later, a 50-foot tall tsunami wave caused by the earthquake arrived at the site. The site was protected by a seawall that was 15 foot tall, so the wave easily flowed over that protective seawall. The ensuing flooding caused the emergency diesel generators to become disabled. They were located in the basements of the building. Maximum protection against earthquakes, but minimum protection against flooding. The floodwaters also disabled a lot of the electrical distribution system, the wires, the circuits that carried the power to equipment throughout the plant. That left the plant without any electrical power except for some batteries that had survived the tsunami. The batteries were sized to last for only 8 hours under the assumption that you'd either reconnect to the electrical grid or fix one of the emergency diesel generators in that time. That condition where all alternating current power was lost and the only thing you had was direct current power from batteries is what's called a station blackout. It had been known for decades that station blackouts are very likely to lead to core damage, and this event followed that script pretty well. Next slide, please. In the situation they were faced, the workers had little options. They had a lot of pumps and a lot of equipment, but no power for any of that to work. The only thing they had left basically were portable pumps and portable generators that were on the backs of trucks, on barges, and so on. The difficulty in using that last ditch effort was that the pressure of those pumps was less than the pressure inside the reactor vessel, and it's hard to push water in against that much pressure. They were unable to lower the pressure inside the containment inside the reactor vessel in order to use these external pumps to move water. Even though the Pacific Ocean was literally a stone's throw away, they were unable to get water into the reactor cores in time to prevent 3 reactor cores from overheating and melting down. The challenges the workers faced were that the earthquake and the tsunami had done quite extensive damage to the infrastructure, to the plant. So the pictures kind of suggest the damage, and these are pictures outside the plant. Inside those buildings, particularly before the walls and the roof blew away, it was dark, it was hot, there were some radiation out there, and the workers were stymied in their efforts to move through the plant and take some of these remedial actions. In addition, they lost virtually all communications equipment, so every time someone went on the plant to check on a pump position or valve position, they had to come back to the control room to tell the operators where things were, and it just slowed down their response. Ultimately, the 3 reactor cores that overheated and melted generated quite a bit of hydrogen as a direct result of that overheating. The hydrogen got into places it shouldn't have been and detonated, which blew away the roof and the walls of units 1, 3, and 4. The picture on the right shows the unit 4 reactor building after the explosion. The benefit, although that's not why they blew up the buildings, but the benefit of that happening is it provided pathways that helicopters and fire trucks from below were able to use to get water into the spent fuel pools. So as bad as Fukushima was with 3 damaged reactor cores, the openings that resulted from that allowed workers to minimize the damage and prevent spent fuel pools from becoming overheated, or the spent fuel in those pools becoming overheated and adding to the problems that the site faced. Next slide, please. So with those 3 reactor cores not getting sufficient cooling water, the pathway from that is pretty well known. The fuel overheats. As the metal tubes that encase the fuel pellets overheat, they generate a lot of hydrogen gas through a chemical reaction. They also generate heat. It's an exothermic reaction, which means as it heats up, the reaction causes that process to get even worse. The cladding started breaking. Here, at the bottom of the picture, you see what's called a fish mouth crack in a metal fuel rod, and you kind of see the fuel pellets inside. It got much worse at Fukushima. It actually overheated and melted. It became more like lava than fish mouth cracks. And the exact location of those reactor cores is known in general, but not specifically, because workers hadn't been able to get inside the containment buildings to figure out where they wandered off to. Next slide, please. As I mentioned earlier, the loss of alternating current power and batteries left the spent fuel pools without cooling as well. The advantage the spent fuel pools had was that there were more water and less decay heat, so workers had more time to deal with that problem than they had to deal with the 1, 2, and 3 reactor cores. They had hours to days instead of seconds to minutes to deal with the problem. Because of the hydrogen explosions, they were able to get water into the spent fuel pools. The major spent fuel pool of concern was the Unit 4 spent fuel pool. It had all of the Unit 4 spent, the reactor core had been offloaded the previous December into the spent fuel pool. It had the most fuel, the hottest fuel, and it was the spent fuel that was going to have a problem if any did. But they were able, as I mentioned, to get water in from above and below to replace the water that was being boiled off and prevent the fuel inside that pool from overheating. Concern about that pool has contributed mightily to the Nuclear Regulatory Commission's recommendation that U.S. citizens evacuate out to 50 miles from the plant. Next slide, please. So with the end, or the end of the beginning, I guess, because it's going to take quite a while to clean up the mess, but they lost 3 reactor cores, melted down. Units 1, 2, and 3 that were operating at the time, they weren't able to adequately cool, and they all 3 overheated and melted down. There were 2 spent fuel pools, Units 3 and Unit 4, that were of primary concern. They were able to prevent fuel damage, significant fuel damage in this core. 3 hydrogen explosions damaged the Unit 1, Unit 3, and Unit 4 reactor building. There was no fuel at all in the Unit 4 reactor core, but Units 3 and Unit 4 shared a common exhaust line, and it's theorized that hydrogen gas from the damaged Unit 3 core went through that shared line into the Unit 4 reactor building and exploded. The picture at the bottom shows the Units 1, 2, 3, and 4 reactor buildings from left to right. Unit 1 is just barely off the screen to the left. Unit 2 did not explode. You can somewhat see some vapor coming from the upside, the far side of the reactor building. When Unit 1 exploded, it opened up a panel in the Unit 2 reactor building, which allowed air to escape, perhaps also some of the hydrogen, and contributed to perhaps it avoiding that outcome. The 3 reactor cores released quite a bit of radioactivity, and much of that got into the air and water, which prompted the evacuation and leads to tens of thousands of people today, more than 3 years later, that still can't go home because of the contamination. And it basically left a footprint that's going to take decades and billions of dollars to undo the damage from our cleanup. Next slide, please. Yeah, I think this is where I turn it over to Ed. Ed, your turn.
Hello, am I unmuted?
You're live.
Okay. So I'd like to talk a little bit first about the state of the site today, because there's still a lot of concern about it. So the reactor operator, TEPCO, says that the reactors are in cold shutdown, which means that the temperatures of the reactor cores are well below the boiling point of water. This makes it easier to keep them cool, and it reduces the risk that there'll be another overheating event that will lead to some sort of catastrophic release. But the consequence is that fresh water has to be continually pumped through the reactor cores and into the spent fuel pools. And because of all the damage that's been done to the reactor vessels, that water is somehow finding its way out of the reactor cores and into the basements of the turbine buildings next door, and eventually into the soil under the site. So these reactors are riddled with holes like Swiss cheese. The problem is no one knows exactly where the holes are, and there's no way to really plug them. At the same time, the site is on the seacoast, and there are hills to the west, and rainwater and flows every day, hundreds of tons of water from the west through the site and into the sea. And some of that water commingles with the radioactive plume that's under the reactors, and it's washing radioactivity into the sea every day. The TEPCO's approach to try to stop this, well, it's a Band-Aid right now. They're trying to pump some of the groundwater upstream of the plant. They just started doing that to reduce the flow of water through the plant, but this is only a very small amount of the total flux of water. In the longer term, meaning over the next few years, they have an ambitious plan to try to freeze the soil around the site and create what's called an ice wall, but that itself has some technical challenges, and it's not clear it's going to work. Decommissioning of the site itself is going to cost more than $10 billion as a current estimate, but that's only a fraction of the total liability that TEPCO is facing. Next slide, please. So what is the human toll of the accident? Well, that's still yet to be seen, but currently there are 160,000 people who were evacuated from the regions around the site as far as 25 miles away because of contamination of the ground by cesium and iodine. The cesium-137 persists in the environment for hundreds of years, and so that's still very much present. Almost 150,000 people are still out, have not been able to return to their homes. And there's a very troubling issue, if you saw the New York Times yesterday, in that as the Japanese government tries to clean up certain areas and declares them clean, they cut off the compensation payments that they're providing to evacuees to allow them to stay in other areas. And that makes them face the choice of returning to a region which may not have been completely decontaminated and is lacking services and is not really a great place to live right now. They have that choice, or the choice of having their compensation. Well, their compensation is going to be cut off, so they really don't have any choice. It's either not having an income anymore or returning to a contaminated home. So this is one consequence which, as more and more areas are declared safe by the government, it's going to become a bigger and bigger problem. Most of the radioactive exposure is probably still in the future. That's going to be people who return to areas where there's more radiation than there used to be, but at levels which the government says it's safe. But that is going to have a health toll, and it's going to cause thousands of cancer deaths in the future. We still have the opportunity to prevent some of those, but the way things are going, it doesn't look like it's going to happen. Next slide, please. Now, one thing our book focuses on is the issue of whether something like that can happen here. And after the accident, the industry and the Nuclear Regulatory Commission strenuously denied that something like Fukushima could happen here. And you see NRC Commissioner Magwood testifying a year after the accident that he just doesn't think it would happen. So we think it's clear that complacency is as prevalent here as in Japan, complacency that led to a lot of decisions being made, bad decisions that contributed to the severity of the accident. And if you look at the safety requirements we have in place now and those that are being put into place, we still don't think there's enough margin for error, and that ignores one of the biggest lessons of Fukushima, is that we don't know. There are still a lot of uncertainties about how bad an event like this can be, and you need to have a big safety margin to compensate for those. Next slide, please. So would we have been ready if Fukushima had struck in the United States? Well, the NRC and the industry said that our plants have what are called severe accident management guidelines, that the staff has procedures that they can deal with core melt accidents. They know what to do, and the Japanese didn't. We had procedures that were put into place after the September 11th attacks to deal with the possibility of an aircraft attack that cut off all power to a site. But it soon became clear that nothing that the U.S. had in place would have made much of a difference if something like Fukushima had happened here. It turns out those guidelines, which are called SAMGs, were voluntary. That means the NRC wasn't able to really review or inspect them in any decisive way, and they certainly couldn't cite or fine the utilities if they seemed inadequate. And it turns out a lot of them were obsolete, had never really been trained on, probably wouldn't have worked. Also, those post 9/11 procedures and equipment that were in place, turns out many of that equipment would not have survived a severe earthquake or flood because it was not designed for that. It was designed to survive a fire from an aircraft crash. This was all confirmed after Fukushima when inspections were conducted, and as a result, the NRC realized that they need to do more. Next slide, please. And so we do have 100 nuclear reactors still operating in the United States. If you just look at the industry's own numbers, the risk of a meltdown, Fukushima-type meltdown, is about 1% per year. That something like that will happen somewhere in the United States, and the containment could fail depending on the type of plant. If it's an ice condenser and a station blackout, that could be up to 100% chance of failure. So that meltdown would result in a radioactive release with near certainty. Next slide, please. I'll skip that. Next slide, please. So even though the NRC insisted that our plants were safe, they still convened a task force to, actually it was President Obama who ordered them to do a review. So they convened a task force to look at whether safety upgrades were needed. And they came back about 3 months later with a 100-page report with 12 detailed improvements. So that kind of was evidence that maybe we had some problems that we need to deal with. And now, as we're approaching 3 years after the task force report came out, the report card is mixed. The NRC is implementing some of the recommendations, but they've watered them down in some important respects. Others have been put on the back burner, and still others have been rejected outright. Next slide, please. So what are some of the actions that are happening? Well, the NRC ordered all the plants to take another look at whether they could withstand the earthquakes or flooding or other natural hazards that their site could actually experience. And it turns out, well, most plants were built many decades ago, and for one reason or another, either it was lack of information about the actual hazards or a change in weather conditions, but in many cases, these plants are now potentially vulnerable to more severe earthquakes or greater flooding than they were originally designed for. The question is, what do you do about that? The NRC also required that that emergency equipment that had been put into place after 9/11, that they upgrade that equipment so it has a better chance of surviving the type of event that it's supposed to be able to help mitigate. But the way that's being implemented raises a lot of questions. The NRC also decided to require that hardened events be made more reliable, so that if the Mark I boiling water reactor had to vent to reduce the pressure to enable emergency cooling water to be injected, that they'd have a better chance of actually making that happen in the station blackout, and they wouldn't have to scramble to try to do it like they did Fukushima. And finally, the NRC required that instrumentation be improved and spent fuel pools, because one of the problems at Fukushima is the loss of instruments meant they had no reliable way to know what was going on in those spent fuel pools, and they became a major distraction. Next slide. So what isn't the NRC doing? Well, the NRC seems to not be pursuing a plan that the task force recommended to take a fresh look at all the accidents that U.S. plants are required to withstand, saying maybe we need to expand the scope to look at things that used to be thought as improbable, but because we don't know how improbable they are, maybe they're a bigger threat than we thought. We need to do that systematically, is what the task force said, but the NRC has essentially put that on the back burner. There's also the issue of expanding emergency planning zones. It was clear after Fukushima that radiation, dangerous levels of radiation, travel a lot further than 10 miles. But the NRC has refused to consider a petition for rulemaking that the Nuclear Information Resource Service file that would have required a modest increase in the emergency planning zone to 25 miles. The NRC's position is, well, if we had to expand the zone during an accident, we could. No one's saying we'll stop at 10 miles, but if you have an ad hoc evacuation of a densely populated urban area with people who had no idea they were at risk until after an accident happens, the likelihood of success is low, in our opinion. Finally, it looks like the NRC is poised not to require the overstuffed spent fuel pools that we have here in the United States from being thinned out by transferring some of that fuel to dry casks, reducing the risk of the spent fuel pool fire if there's a loss of cooling water. The NRC staff has looked at a very, very narrow set of potential events and said there's no risk with the current spent fuel pools, and it looks like the Commission's inclined to agree. Next slide. Very briefly now, so what about new reactors? You've got the AP1000 under construction at Vogtle and at Summer. Westinghouse was boasting that this plant was so safe that it would have been able to withstand Fukushima. In our assessment, that's a lot of baloney. And the real question is, what is the plant designed to withstand? Because no reactor is going to, no designer is going to build plants that are much more robust than what the requirements actually say they need to do. And that's the case with the AP1000. It has some features that look better, but it has others that look worse. And we don't think in the overall assessment that plant is safer than current reactors. However, the NRC has given it a free pass. All the operating reactors are required to show that they have reliable equipment and procedures that can keep the plant from melting down, the spent fuel from overheating, until cavalry arrives from off-site. They're required to do that analysis, but the AP1000 is not required to do that analysis, and that's because it claims that it already has systems that can withstand a station blackout for 72 hours. But those systems are only designed to the same earthquake and flooding standards that any other plant is designed for. So if they experience something worse, those systems may not work. But we're not going to know that because the NRC isn't requiring them to analyze that. Next slide, please. And finally, what about small modular reactors? Another reactor that their vendors boast are so safe they could have withstood Fukushima. But the same logic applies. Just because a reactor is smaller doesn't necessarily mean that it's safer. And it really depends on the requirements that address, that cover it. So, and then there's the pressure of trying to make a reactor both safer and cheaper at the same time. an SMR actually would generate very, very expensive power because you lose what's called economies of scale. As a reactor gets smaller, the unit price of electricity it generates increases. So the SMR vendors were trying to both reduce cost and what they claim make the reactor safer, but you really can't have both. And I think that Babcock and Wilcox finally appreciated that by essentially pulling the plug on the development of the MPower small modular reactor. Even though they're denying that the program's dead, they're busy laying off people in Virginia. They've reduced their projected spending by a big factor, and it looks like, I would say, there's very little prospect for it. Next slide. And I think I addressed this one, so next slide, please. Okay, so now I'm going to turn it over to Susan. Thank you.
Thank you, Ed, and thanks everyone for joining us today. I came to this project as the storyteller. I'm a journalist, as you were told, and I saw this as a technological disaster, but one with a very human face. And I think we're seeing more and more of the human side of what the long-term consequences are. About 40% of all Americans live within 50 miles of a nuclear plant. That amounts to about 120 million people. That fact alone should answer the question, why should we care about nuclear safety? Nuclear safety has long been debated in hypothetical terms, but what we saw on our television screens and in web videos and stuff was an accident that was playing out in real time. And I think the world saw exactly what could happen, and that this very carefully crafted myth of safety unraveled before their eyes. We just watched transfixed as events just kept worsening and worsening. So why do we care? Because we write that this was not a Japanese nuclear accident. It was a nuclear accident that happened to have occurred in Japan. As Ed and Dave have both said, both U.S. nuclear plants are vulnerable to catastrophic natural disasters, to multiple system failures, and certainly to large terrorist attacks. U.S. nuclear plants are not much better equipped than Japanese plants to cope with severe accidents. U.S. emergency plans are not designed to protect the public after Fukushima-scale accidents or fully address the problem of long-term land contamination. The decisions have been made largely by nuclear insiders, and the public has really largely been shut out of much of the debate. And part of our reason for writing this book was to not only detail the accident, but also to detail just how little the public has had to say on the decisions historically that have been made on nuclear regulation and nuclear operations across the board. So we really tried to put a human face on our story that I think shows that all of the assurances of the proponents of nuclear power have rung very hollow. And I think that by telling a story with a very strong narrative, which is what we tried to do by explaining the drama that was going on, not only within the plant itself, but also within the Nuclear Regulatory Commission. And we tell much of our story through the lens of the NRC, which was by and large just flummoxed by the accident as it unfolded, and they scrambled very, very hard to learn what was going on and to better understand it. But for an agency that is charged with protecting the public health and safety in this country, as well as for Americans that were over in Japan, they really were largely caught unprepared. And I think one of our messages in the book is that this is going to happen again and again, and it really is only a matter of time, and that the NRC needs to be pushed in a direction that this myth of safety is reevaluated from top to bottom, and the lessons of Fukushima be not only acknowledged but be put in place and quickly. So thank you very much, and I think we all are eager to hear your questions.
Thank you, Susan. This is Sarah Barzak again, and I just want to remind all the folks attending that you can submit questions via the control panel that you can see on your screen. There's a little line that says questions, and you can hit the little drop-down arrow and type it in. So as you come up with those, please send those along. I have a few to start out with, and I think I'll start this one towards Susan, and if Ed and Dave want to chime in as well, that would be great. The question is, in your opinion, Susan, what has changed since 3 Mile Island accident in 1979 and the Chernobyl disaster in the former Soviet Union? That was actually just 28 years ago this past Saturday, April 26th. So what has changed in terms of perhaps the industry and government response to accidents, and perhaps, in your opinion, the media coverage?
I feel comfortable talking about the media coverage specifically, and would defer to Ed or Dave really to talk more specifically on regulations. I think having been through 3 Mile Island and now watching as the Fukushima accident unfolded, I think not much has changed. There really was a lack of transparency. There was a push by all of those involved, both within the utility and within the Japanese government during Fukushima, to offer reassurances that really had very little basis in fact, and that was true at 3 Mile Island as well. So what happened, and we saw this very clearly at Fukushima, because of the presence of social media and the internet, that people were left on their own to scramble for information that they could trust, because they had lost all confidence in getting a straight story from the officials in charge. Back during 3 Mile Island, it was much more difficult to get information, and trust is essential. And we write about this, that people became very fearful, rightfully so, because they no longer trusted those that were charged with protecting their health and safety. What has happened with media coverage? I think the media is a lot more skeptical. In the book, we talk about a quote from Peter Bradford, a former NRC commissioner, who says that what we really need is more skeptical regulation. And I think what the media has done is to perhaps approach some of the assurances about nuclear safety with more skepticism. That's in part due to organizations like yours, organizations like the Union of Concerned Scientists, and others who very carefully follow these issues and lay out their concerns in a way that the public can grasp the information and understand it, and then hopefully act.
Great. Thank you, Susan. Ed or Dave, if you wanted to follow up with anything on that question, feel free. If not, we can move on.
I'm okay with moving on.
Okay. Okay. Another question, and maybe this is Ed and Dave. What country or countries have taken notice in terms of regulatory changes or maybe this increased scrutiny or skepticism? Are there any models out there potentially for the U.S. to look towards?
Yeah, this is Ed. I could start with that. Well, first of all, of course, Japan has revamped its own regulatory system, and all their nuclear reactors are currently shut down, but the current government wants to restart at least a big fraction of them. They've created a new regulatory agency which is supposed to be more independent than the previous one, but it's not really clear that's shaping up that way. But they've come up with a pretty comprehensive set of new procedures and regulations on the books that would greatly increase the safety margins for existing reactors and require significant upgrades before they could be restarted. But the problem is that there's so much political pressure now that it's not clear they're going to follow through with all the good things that they put down on paper. Now, France is an interesting case. France has nuclear power is a huge part of its energy supply, and they seem to be taking the Fukushima threat pretty seriously, and their approach differs from the U.S. The U.S. approach is something called FLEX, which is that each plant would add some additional emergency equipment and put it in various places around the plant and hope that no matter what happens, that some of that equipment is going to survive and they'll be able to use it to help save the plant. So in other words, if you're worried about an earthquake and a flood, you put the one piece of equipment in a building that's hardened against earthquakes to some extent, and the other you put it on a high shelf, and you hope that you don't get both at the same time, which of course they did at Fukushima. So it's not really a robust strategy. In France, however, they say, well, we need to put that equipment, we need to harden it against an event which is worse than the reactor itself is designed to withstand, and that's what they call the hardened core. And the other thing that France is doing is they're going to have 4 regional response centers that can dispatch additional emergency equipment to any plant in the country, and the idea is to be able to handle, I think, 2 or even 3 simultaneous accidents with the equipment from these response centers. In the U.S., which is a much larger country and has more reactors that are spread out further, they're only going to have 2 regional response centers, one near Memphis and the other near Phoenix. And so, just comparing the 2, looks like France is really taking a more serious approach to this than the U.S. is.
Thank you. That's very informative. And actually, as you spoke, some of the comments that you made brought up 2 different power plants that are in the southeast. One plant, a Coney 3-reactor facility that Duke owns in South Carolina, and then the ice condenser reactors that we have at a variety of sites in the southeast. One under construction, TVA's Watts Bar 2 in Tennessee. So the question was whether you could say anything more about a station blackout at an ice condenser reactor, which could represent 100% risk of meltdown and containment failure. And then maybe Dave, because I've heard you speak to it before, maybe touching on the Oconee concerns in particular.
Sure. So about the ice condensers, these are sort of the pressurized water reactor analogs of the Mark I boiling water reactor. The idea is you can have a much smaller and a much weaker containment if you have some system that could condensed steam that's generated in the loss of coolant accident reduce the steam pressure against the containment. But in both the Mark I's and the ice condensers, when they were first designed and built, the designers didn't worry about hydrogen explosions. And so those types of plants both had to be retrofitted after this realization. Mark I boiling water reactors were, the containments were filled with an inert gas that's supposed to prevent hydrogen explosion. Then ice condensers, the NRC required that they install spark plugs, which are called hydrogen igniters, and the idea is that you can burn off hydrogen before it gets to a concentration that could actually be explosive. Problem is those igniters require alternating current power. So if you had a station blackout, you could have both a core melt and loss of the igniters that would prevent a hydrogen explosion. And back in the late 90s, Indian National Laboratories did a calculation, a report, where they predicted that for certain plants, certain ice condensers, you have up to 100% risk of containment failure in a station blackout. The NRC was forced to take a look at that issue again, and the staff actually said, well, it would make sense to upgrade the emergency power to the hydrogen igniters, so even in a blackout you can still prevent the containment from blowing up. And they were ready to actually impose a new regulation on the industry, but the industry cried foul. They said, oh, you know, you can't just go out to Walmart and buy new diesel generators. You know, you have to build these really robust, seismically protected diesels, and it's going to cost a lot more than what you said. And if you do the cost-benefit analysis right, you find out it doesn't pass the cost-benefit test. So the NRC backed down and said, okay, well, why don't you just do it voluntarily, and we'll be satisfied with that. And so they went out and they bought diesel generators at Walmart.
My goodness.
And the NRC had no regulatory control over those because it did not create a regulation to govern them. And this is one of the things that the task force, well, the NRC asked the staff to look at this idea. We need to come up with a consistent new set of regulations to protect against these kinds of severe accidents. And that report actually pointed out this problem and said, well, if we had had the better system back then, this never would have happened. So they're essentially admitting that they made a mistake, but it looks like the Commission is not learning lessons from this, and they're not going forward with a new set of requirements that would make better, more intelligent decisions. And so as a result, the ice condensers are still protected only with voluntary measures against hydrogen explosion.
Wow, very interesting. Dave, do you want to add a little bit on Oconee?
Yeah, I'd be glad to. Ed mentioned earlier that the Commission said that it can't happen here. He quoted Commissioner Magwood as saying that he just doesn't think it could happen here. What concerns us, and we describe it in the book, is that 9 months before Fukushima, in June of 2010, the NRC issued a secret order to the owner of the Oconee plant to take steps to better protect that plant against flooding damage. The Oconee plant in South Carolina is located about 22 miles downriver of the Jocassee Dam. Calculations by the owner and confirmed by the NRC concluded that if that dam failed, there was a 100% chance that all 3 reactors at Oconee would melt down within about 8 hours, and the containment would fail in about 59 hours. Very close to the Fukushima timelines. That hazard is what led the NRC to issue the order in June of 2010, again 9 months before Fukushima. So it could happen here. That's why they issued the order. They were trying to protect it, guard against it happening here. For them to testify to the Senate that it couldn't happen here is disingenuous at best, dishonest at worst. But bottom line, regardless of whether they lied or misspoke or had a mind lapse, the problems at Oconee are still not fixed today. The timeline that the NRC ordered in 2010 for fixing those problems was delayed by Fukushima and an event that caused flooding damage to 3 reactors. So instead of accelerating the fixes, they put the brakes on them, and they still, to this day, have not entirely fixed the problems at Oconee. And that's safety IOUs don't protect anybody.
Thank you, Dave. Thanks, Ed, too. We have a question asking for your opinions, and the statement was, in your opinion, does the tragedy of Fukushima underscore the opinion that nuclear energy is not, quote unquote, clean energy? And I do want to sort of answer that a little bit by pointing people to page 22 of the book, which is a page that I had turned the corner down when I read it, because it was in the book, it was talking about the decision to vent the radioactive steam as the accident was unfolding. And the little line said, for the nuclear power establishment, the decision to vent radioactive steam holds serious implications. Releasing radiation into the environment demonstrates unequivocally to the public that this form of generating electricity is not as clean and safe as the industry's public reassurances and promotional campaigns proclaim. So I would definitely say read the book, because there's many instances of that. But Ed, Susan, or Dave, would you like to comment on the question about nuclear energy not being the quote-unquote clean energy source that proponents claim it to be?
Well, this is Dave. I can speak to an anecdote. Shortly after I joined UCS in the late 90s, I was at a conference that Joe Colvin, who was then the head of the Nuclear Energy Institute, the trade group for the nuclear industry, was also speaking at. And he spoke saying that nuclear power is the only green energy source around, not one of the major ones, the only one around. So I went up to him afterwards and introduced myself, because we hadn't met at that time, and said his comment initially confused me because I didn't necessarily agree, but then I came around. So he was a little wary. You could tell he was, from his body language, he wasn't sure. And I said, look at Chernobyl. There hasn't been any industrial development about 30 miles around that plant since 1986, and nobody can go in that region. So it's like a park that nobody can visit. So it's clean in that sense. In a greater context, nuclear power is something that you can't have an 80% success rate. You have to be successful 100% of the time, because one bad day can wipe out decades of good days, and no other energy technology has that risk-reward benefit. So Fukushima didn't, show us that. It reminded us of that dynamic.
Thank you. Another question that came in, I'll read it because it highlights some things. It says 4 separate reports, including one from TEPCO and the 2012 Japanese Diet Report, indicated that radiation monitors and alarms went off and pipes were cracked and leaking water before the tsunami hit, suggesting greater earthquake damage had occurred than has been admitted to. Do you have more information on these reports indicating that the earthquake did more damage than it is being given credit for, and that the Mark I reactors are more vulnerable than admitted? This also has implications for what areas in plant improvements are warranted.
This is Ed. We haven't seen any evidence that would really suggest that you certainly don't need to postulate earthquake damage to explain what happened. The flooding and causing the station blackout was really more than enough. So it's very hard to prove, the negative, what would have happened if the flood didn't occur. The latest analysis from TEPCO seemed to disprove the theory that there was a leak, a large leak that was caused in that short window between the earthquake and the tsunami. But again, until there's a full investigation of the damage within the plant, it's really hard to say one way or another. In effect, it doesn't really matter that much, because our position is that a plant has to be designed and operated to withstand the most severe natural disaster that it may face, plus some safety margin for uncertainty. And so you need to take into account the seismic and the flooding and all the potential natural disaster risks, and you need to assume when you don't know something that the potential is that it can fail. So you need to take a conservative approach. The historical analysis will provide some insight, but I don't think it'll change that view.
Okay, thank you, Ed. This next question maybe is just to underscore what you already said, so you may have a very short answer, but I think it's important to make sure people are clear on this when they walk away from the webinar. The question is the NRC still accepting the false assumption in environmental impact statements for nuclear reactors that the chances of a massive release of radiation are so low that they do not have to consider the environmental consequences of such a major accident?
Well, this is Ed again. I think what really is the attitude is that you're required to analyze them. I mean, an environmental impact statement, you need to analyze them, but there's no reason to do anything about them. NEPA cannot force you to, if you find that there's some large environmental consequence from a low probability accident, as long as you've done the analysis, then there's no legal requirement that you do something about it, and that's something that we think needs to change. That there has to be some mechanism for addressing and mitigating extreme environmental consequences if they're discovered or analyzed in environmental impact statement.
Okay, thank you. I know we're coming up to the top of the hour. There are a few more questions here. And how about I just take some of them I can quickly wrap together. So how about just two more questions, and then we'll the additional questions could be answered via email. Although it looks like somebody on the phone may already be getting a question by phone. Anyway, one of them is dealing with what is anything being done to treat all the radioactive water on site? I know they had talked about the groundwater being pumped up above the plant, but in terms of all the water that's being stored on site in giant tanks, are they going to treat it in some way? What is the plan?
Well, this is Ed. The water in the tanks has already been partially treated. They're pumping water out of the reactor basements and putting it through a process which removes most of the cesium-137, and that's being concentrated and stored separately. So the water in the tanks has most of the cesium-137 removed, but it doesn't. The process they're using doesn't remove anything else. So it has high concentrations of strontium-90 and tritium and some other isotopes. They've been trying to get another process to work, which they call ALPS, which would remove strontium and some of the other stuff, but they've been running into significant problems with that, and it keeps failing. So the plan is eventually, if that ever works, to treat the water, to concentrate and filter more of the radioactivity, and eventually some people, including Lake Barrett, who's an American advisor, pushing them to release that water into the sea, and that's they've already built more than 1,000 tanks storing this water, and they want to build 1,000 more, and that's going to be a legacy for the site that they're going to have to deal with over time, one way or another. But right now the water is only being partially filtered until they can fix that system.
Thank you, Ed. This is Sarah, and I'm going to turn it back over to Erin. There were still a couple questions left, but we're after 1 o'clock now, and I want to be sensitive to the schedules of our speakers and all the people that participated by phone. Thank you for so many of you staying on for the full webinar and to engage in the question and answer period. Erin?
Sure. Thanks, Sarah. And thank you, Ed, Dave, and Susan. And for all of you for being with us today and for your thoughtful questions. I did want to mention that today's presentation will be has been recorded and will be available on the webinar archive page of our website, cleanenergy.org. And we will also send you a link to that recording in the follow-up that we will send later this week. So we appreciate your support and interest and hope that you'll join us again.
Thank you.
Thanks, guys.
Thank you.